Padua. I'm a cosmologist, and in particular, I study different tests of modified gravity models and dark energy models. So what I will talk about is a particular class of modified gravity models, which is called camouflage. Let me first do a little bit of introduction, since the audience is quite wide. So we have, in cosmology, we have a standard model which is called lambda CDM. This model was first formulated in the last century, and it assumes a universe which is shows homogeneity and isotropy on large scales, and is in constant expansion. So from about 20 years, we know that the universe expansion is actually accelerated, and we want to explain this observation. So the standard picture assumes the presence of a cosmological constant, which, however, is quite a bit in tension with the value predicted by particle physics. So we are looking for alternatives. And one of the possible alternatives is to think that the general relativity is modified on large scales to account for this acceleration of the expansion. So one possible model of modified gravity is this camouflage model, which assumes the presence of a scalar field, which is non-minimally coupled to the matter fields outside through this conformal rescaling of the matrix. So what are the main ingredients in this Lagrangian? This conformal coupling here, which sets the coupling between the scalar field and the matrix, and this kinetic function k, which represents the non-standard kinetic term for this scalar field. To fix a particular model of camouflage, you have to choose the form for this coupling function and this kinetic function, which are both functions of the scalar field and of the scale factor A. So these models have been mapped in this effective field theory of dark energy, which is a unified description of many models of modified gravity. And through this mapping, so you can see that some of the operators are switched on and some others are switched off by camouflage. So through this mapping, we could implement camouflage models in this code, which is called EFT-CAMB. EFT-CAMB is a Boltzmann-Einstein solver which solves the full coupled Boltzmann-Einstein equations at the linear order. And so it can compute many cosmological observables, like, for instance, the CMB power spectrum, which is one of the main observables in cosmology. And we can do this for not only for the lambda CDM, so for the standard cosmological model, but only for camouflage, thanks to this code. So this is a bit of phenomenology. You can see here that camouflage models affect both the background expansion and linear perturbation evolution. You can see here that the Friedmann equation, which is the equation that governs the expansion of the universe, is modified in camouflage models by the addition of this factor here, which is a function of the coupling function, and of this factor here, which is a function of both the coupling function and the kinetic term. So you can see there is an additional energy source due to the scalar field in the Friedmann equation. one other important function is this epsilon 2, which is basically the logarithmic derivative of the coupling function with respect to the state factor, and this accounts for a running of the Planck mass in camouflage models. So the Planck mass is not constant, but evolves with time in camouflage models. About linear perturbations, so this is the Newtonian gauge metric. So we expand the metrics and these are the two perturbations, phi and psi. So we see that in camouflage model you have a late time anisotropic stress. So while in general relativity these two factors are equal today, in camouflage they are not, and we can observe the effect of this modification. So also the Poisson equation is modified, is no more the standard one, and you can see is modified by this factor here that we call mu, and also the lensing potential. So the way the lensing is the effect due to the fact that photons follows geodesics in their path, and this effect is modified also in camouflage models with respect to standard GR. Here you can see some plot. This is the relative deviation of the Hubble factor with respect to lambda CDM, and you can see that it is different from 0 for different models of camouflage. And here on the right you can see the evolution of the two potentials, psi and phi, that I showed before, these two here. And you can see the black line is the lambda CDM solution, while the green line is the camouflage solution. And you can see that there is a difference at redshift 0. There is a substantial difference between the two. So to study these models, we have to fix the form of the coupling function and of the kinetic function. We do this by parameterizing the models and introducing 5 additional parameters besides the one of the lambda CDM model. So 3 of these parameters, 2 of these parameters, gamma u and alpha u, controls the form of the kinetic function, while the other 3, m, gamma a, and epsilon to 0, governs the form of the coupling function. However, there is a main parameter in this game, which is the epsilon to 0, here the last one, which sets the lambda CDM limit for this camouflage model. So when you set epsilon to 0 equal to 0, you recover the standard GR. And this gives basically all the deviation between the camouflage model and the standard GR. So this is the effect of camouflage on the CMB temperature power spectrum. So the CMB power spectrum is a way to statistically describe the anisotropy, the temperature anisotropy that we see in the map of the cosmic microwave background. And we see that the red curve here is the lambda CDM solution, while the green curve is the camouflage solution. You see that there is an horizontal shift of the acoustic peaks of the power spectrum. This is due to a change in the distance to last scattering surface and a change in the sound horizon too. So these two effects combined gives you a shift toward the higher multiples of the CMB power spectrum. This is due to the modification of the expansion history that you have in camouflage models. So since the Hubble rate does never recover the lambda CDM solution, you see this kind of effect in the CMB power spectrum. So we constructed some model. We try to recover the lambda CDM background expansion within camouflage model, where we asked ourselves if it is possible to reproduce a lambda CDM-like expansion, so a lambda CDM Hubble rate within camouflage models. So skipping all the details here, we arrived to a form for the kinetic function that allows to reproduce a lambda CDM Friedman equation. But we cannot do it at every redshift because we have to impose some stability conditions in order to not have, for instance, negative kinetic energy in camouflage models. So you have some constraint, theoretical constraint that you have to impose within these models. So at the end we end up with the model which we call K-mimic, which can reproduce the lambda CDM background expansion at very high redshift, but you still have a deviation here during the matter-dominated epoch. So this is the violet curve is the camouflage model, while the cyan curve is the K-mimic solution. And you can see that you still have a deviation with respect to lambda CDM. So it is not possible to exactly reproduce a lambda CDM background expansion in camouflage. This is the evolution of the scalar field energy density with respect to the redshift for camouflage and K-mimic. And you can see that in camouflage, the scalar field energy density becomes negligible after redshift 1, redshift 2, while in K-mimic models, the one that we constructed with the previous in the previous slide, you have a scalar field which is never negligible, so which gives always a contribution to the density, to the energy density of the universe. So there are some different observational imprints for camouflage and K-mimic models. In camouflage, you see the shift in the peaks that I was telling before, the horizontal shift, while in K-mimic you don't have horizontal shift because you recover the lambda CDM background expansion at very high redshift, but you have a strong suppression of the growth of matter perturbation. So the matter perturbation growth is strongly suppressed, and you can see this in the CMB power spectrum with an enhancement of the early integrated Sachs-Wolf effect, and also the acoustic peaks are suppressed because in K-mimic you have less gravitational force because the coupling in K-mimic is less than 1, and so the effective gravitational constant is lower than in the GR case. So we studied both these models, and we ran some Markov chain Monte Carlo simulation, okay, and this is the effect for instance, sorry, for the CMB lensing power spectrum. The CMB lensing is another observable that you can compute with the EFT-CAMB. So this tells you about the distribution of the gravitational potential between the last scattering surface and us. And you see that in camouflage this is almost unchanged with respect to lambda CDM. These are different models. here, while for K-mimic, this is strongly suppressed with respect to lambda CDM. This is again an effect of the gross suppression of matter perturbation. So you have less matter perturbation, you have less gravitational potential in K-mimic, and so you have a suppression of the CMB lensing. All these effects allows us to constrain the parameters of the models. So we run some Monte Carlo Markov chain using different data set. We used for the CMB and CMB lensing the Planck 2015 release. Then we had also supernovae and BAO measurement. BAO were taken from BOSS survey and SDSS. And we also had some a local measurement of the Hubble constant H0. So you can see here that the epsilon to 0 parameter is constrained to be close to 0, so we are close to the GR limit. But when we add the H0 measurement, we get larger error bars here. So there is a degeneracy basically between H0 and the epsilon to 0 parameter, because both the parameters can shift the peaks of the CMB power spectrum, and basically this degeneracy is useful because it helps to solve a tension between the CMB measurement and the local measurement, which predicts slightly different values for the H0 parameter in lambda CDM. In camouflage, this tension is reduced because you have the possibility of taking a larger value of H0. These are the results for K-mimic, and you can see that here the epsilon to 0 parameter is much strongly constrained in K-mimic, so these models are really pushed toward the GR limit, and we can say that they are ruled out, basically, because of the strong growth suppression. Indeed, when you add so that's it for these models. So there is also an evidence of the growth suppression when you look at the sigma 8 parameter, which is lower than the lambda CDM case here. So we ran also some Fisher matrix forecast for core, which will be a future CMB survey, and we see that we could improve our constraint by an order of magnitude, more or less. These are my conclusions. So we have analyzed the camouflage models considering a generic parameterization of the kinetic and coupling function, and K-mimic models fixing the kinetic function to stay close to lambda CDM to reproduce the background evolution of lambda CDM. So camouflage predicts an early time deviation in the background and the horizontal shift in the CMB acoustic peaks, while K-mimic shows a deviation, still a deviation in the CMB power spectrum and the strong growth suppression. So they are very constrained by data. So the cosmological probes that we have analyzed are complementary to solar system tests, because these models can be also constrained by solar system tests. Indeed, they have to recover basically the GR solution within the solar system, because within the solar system the gravity is very well tested. But we obtain competitive results with the cosmological constraints. And the camouflage models remarkably can alleviate the tension on the Hubble constant parameter that you find in the standard lambda CDM model. So the ongoing work is produce forecast for the Euclid survey, which will be is a very important survey that will be launched in the 2020 about. And also analyze the genesis with the massive neutrinos that we didn't take in account in our model. But they also can shift the acoustic peaks, so they can be degenerate with the camouflage parameters. Thank you.
We start for one question.
So I guess when you do your action, right?
Yeah.
The first that is in the Einstein, right? Your action.
Yes. Yes.
Okay. So
yes.
probably your max Planck constant is running around during time because you have some non-minimal couplings when you go to the Jordan prime, right?
Exactly. Exactly.
And when you put your action at the end in the Jordan prime, are you able to separate totally or to isolate the matter action? Or at the end your matter action also has some coupling with it?
No, it always has some coupling. So that's what gives you the difference between simple K-essence models and camouflage models.
Right.
So in K-essence you don't have this non-minimal coupling.
So I guess that is the reason why you get these photons going on trajectories that are not precisely geodesic of the space.
Yes. Yes.
Okay.
Thanks to the speaker again. The next speaker is Aldi, and her talk is about rotation in galaxy clusters from music simulations with the kinetic Sunayev-Zeldovich effect.
Good morning, everyone. I am Aldi, and I would like to present you recent work I did in collaboration with Marco De Verris, Federico Sembolini, Gustavo Lietes, with Wang Hui and Luca Lamagna on the detection of rotation in galaxy clusters from music simulations using the kinetic Sunayev-Zeldovich effect. So first of all, I will give a brief introduction and some motivations for studying this topic. And in particular, I will focus on the use of the kinetic Sunayev-Zeldovich effect for probing the possible rotation of the ICM in galaxy clusters. And finally, I will give you some results and draw my conclusions and future perspective. So the main targets of this study are galaxy clusters that are the largest gravitationally bound and virialized structures that form in the universe. They extend over radial radii of the order of few to tens of megaparsecs, with virial masses from 10 to the 13 to 10 to the 15 solar masses, and they can be observable at redshifts between 10 to the minus 2 to about 1. Despite the name, galaxies are the less abundant component in the mass budget of galaxy clusters. So they are about 3% of the total mass, and they can be seen in the optical band, as I'm showing here, for example, for this cluster. We also have a 17% of hot gas that I'm also gonna call very frequently ICM, or intracluster medium, which is visible through the Bremsstrahlung emission in X-rays or in the microwave region because of the Sunayev-Zeldovich effect. And we have an 80% of dark matter that can be mapped through gravitational lensing. The masses of galaxy clusters are very important for constraining some cosmological parameters related to the measurement, and we have some observational approaches for detecting the value of cluster masses. So if we assume that the intracluster medium is a collisional fluid in a steady state configuration, we can combine Poisson equation and Euler equation to get the following equation here, which basically is related to the gradient of the thermal pressure, which is due to the random thermal motions of the gas within the cluster. And if not vanishing, we also have to take into account a dynamical term, which is this one here, that acts as an effective gradient of the pressure associated to all ordered non-thermal motions that could be, for example, streaming or infall, or in the specific case we're going to study, rotation, to investigate the possibility of detection of rotation in clusters from the ECM or from the galaxy members. We have different examples in the literature exploiting the three different bands in which we can observe galaxy clusters, but the feasibility of these procedures are still very challenging because we need very high angular resolutions and sensitivities. So for the moment we can take advantage of the presence of large catalogs of simulated galaxy clusters to conduct preliminary studies on the feasibility of these measurements. And in particular, in our work, we are referring to the MUSIC catalog, which is one of the largest available, with more than 500 galaxy clusters, resimulated from two parent simulations, the Mare Nostrum universe and the multiverse simulation, that follow the evolution of gas and dark matter particles with the gadgetry hydrodynamical code. So we have here we're going to focus just on a small data set of clusters at redshift 0 that we have selected according to in a relaxed dynamical state, and for our purpose of studying rotation, they also have to have a high spin parameter of the gas, which is, as I mentioned, this indicator that gives the ratio between the rotational energy and the total energy of the cluster. And in this plot here, which is taken by a complementary paper we did before for studying the coherent motion of dark matter and gas in the very same dataset, I'm showing on the x-axis the values of the spin parameter of the gas, and on the y-axis the value of the angle between the two angular momenta of the gas and the dark matter. But what is important to see here is that above the given threshold, represented by this dashed orange line, we have very few objects, and they become even less if we restrict the attention to the relaxed ones, which are the blue points. So basically, we end up with the dataset of 6 possible candidates for finding rotation. And from this work, we also found another interesting result, that is to say that when we analyze the profiles of the tangential velocity of the gas and we average the profiles from the simulation data along the cluster radius for the 6 clusters we saw above, represented by the blue points here, we find a good agreement with the particular model for the rotation, which is different from a solid body one, which we call BP2B model, and is given by this equation written in red here, in which we can see the presence of two free parameters, namely that are the scale radius R0 and the scale velocity BP0, given by the red curves here. They are the best fit to the data. So our next purpose is to find whether it is possible to reconstruct this profile and to derive the values of the parameters for this model by using some observational probe. And we decided to do that in the microwave region using the kinetic Sunyaev-Zeldovich effect. So first of all, the Sunyaev-Zeldovich effect is just the inverse Compton scattering of the photons of the cosmic microwave background as they propagate through clusters of galaxies and interact with the free, highly energetic electrons. So basically, the net effect from the Comptonization can be seen as a spectral distortion of the CMB black body spectrum, which is just due to the redistribution of the energy of the photons. So we can see, for example, here a magnification of the effect. The black curve is the original Ampere curve, let's say CMB spectrum, and the blue curve is the exaggeration of the effect from the SD interaction. So we see that basically the intensity of the radiation decreases or increases depending on the frequency. In particular, we can distinguish two components, the thermal and the kinetic SZ. The thermal SZ has a spectral dependence given by this function here, g of x, which is this one, that gives indeed the decrease and the increase of the intensity relatively to this cutoff frequency, which is 217 gigahertz if the electrons are taken as non-relativistic, and is proportional from a physical point of view to the integrated pressure of the electrons in the gas. But what is of interest for us is the kinetic component, because it has a dependence on the projection of the ICM velocity of the line of sight, as is shown here, while the spectral behavior is basically the same of CMB, because this function here is essentially Planckian across the different frequencies. It is important to notice that the relative amplitude between the two components of the FZ effect is of the order of few percent, since it is proportional to the ratio. Here I'm just going to show you, observationally speaking, how we can detect this effect. So these 6 maps here are 6 different projections, and these lines here of the maps, purple lines are taken along on the data maps, while the black curves are the cuts on the best fit corresponding to those projections. And we see that basically the amplitude of the dipole is not significantly varying from one line of sight to another. We can also notice that at some projections we have these small scale outliers here, extending over scales smaller than the dipole one, that do not affect significantly the overall structure of the signal. Basically the amplitude that we recover when averaged over the line of sight is reported in the middle column of the table. So we see that we expect that if a rotation is present, it should contribute with a signal of the order of few tens of microkelvin, which is also in agreement with previous estimates from the literature. And if we are going to compare with the maximum amplitude of the signal, I'm reporting here on the right column, from the total KSE contribution given by the dipole and the bulk, we see that the ratio between the two is of the order of 23%. So we have a contribution from a rotation to the KSE, which is not so important, but it's still there in any case, and in principle it could be detected. Just to finish, I'm showing you also another good result of this analysis, which is the recovery of the values of the bulk velocity of the cluster projected on the different lines of sight. Here I'm showing the results for all the 6 clusters in the data set. So the purple dots are the values retrieved from the best fit, and the black ones are the ones from the true simulation data. So except for some cases we have relatively small deviations of the order of few tens of percent, meaning that we are able in principle to give some constraints on the ICM velocity projected on the line of sight, which with other observational probes of the velocity could be helpful for constraining the 3D velocity map of the velocity field of the cluster. So basically we can conclude that our procedure has given good results for what we expected to be the rotational contribution in our selected clusters. But to think to an effective application of this procedure to real objects, we still have to take into account properly some specific requirements for the instrumentation, based most of all on high angular resolution and sensitivity. One of the next developments of this work will be, of course, accounting for the full pipeline of the good candidate instrument, which would be the NICA-2 camera, including all possible sources of contamination coming both from the instrumental setup or from astrophysical contaminants, which are the major problem affecting the detection of the KSE. And as a part of a larger project, we are also developing the investigation of the rotation through complementary probes in X-ray and optical wavelengths to see whether we get consistent results for the very same data set. So thank you for your attention. This is the archive identifier of the paper if you want to have more details. Thank you.
Questions? Please.
So you have studied the kinematics of the gas in galaxy clusters. Do you think it can be helpful for instance, to add also information like the peculiar velocity of galaxies, for instance, to disentangle between the bulk motion and the rotational motion?
Yes, actually, we are currently investigating what is the role of galaxies in the context of the possible rotation of the gas. In particular, we are trying to understand whether the two baryonic components could co-rotate. So, ideally, if we can establish that, we can use the KSZ also to recover the bulk velocity of the galaxy. This is still under investigation. We got some unclear results, let's say. But we are trying to, of course, to look for a correlation between the motions of the two components, though they are very different.
But the bulk motion should be similar. Or it's too naive to say?
No, it's possible that galaxies have some higher velocities actually. And it is not so trivial, let's say, to assume that they should have exactly the same motion. For the dark matter is somehow expected, and indeed we found that the two components should co-rotate because they are diffuse components. But galaxies have all other physics processes in which they are involved, and so it is more difficult to say. They should be like more rotating than the gas.
Thank you.
The questions? Okay. Nice to speak again. The next speaker is Elia Kiragucha, and his talk is about the relation between the X-ray, UV ratio, and optical luminosity in AGN and its integration.
Così? So, good morning, I am Elia Kiragucha, and today I will show you my progress on the study of the relation between the X-ray to UV ratio and the optical UV luminosity in AGN and its dispersion. So, we will see what actually is an active galactic nucleus. We will see what is the origin of the optical UV and the X-ray emission in AGN. I will show you something about the relation between the X-ray to UV ratio and the optical UV luminosity. I will show you the sample I used to perform my data analysis, and last but not least, I will show you why it is so important to study this relation. Okay? So let's start from the first point. What is an AGN? AGNs are among the most energetic phenomena in the extragalactic universe, and their physics is ruled by an accreting supermassive black hole at their center. The main properties are that their physics, their emission is due to both thermal and non-thermal radiative processes. Their spectra are characterized by broad emission lines, as you can see from the plot on the left, which is a focus on the optical optical UV range of a typical AGN spectrum. They are highly variable, both considering lines and continuum emission, and they are high luminosity systems. Okay, and from the plot on the top, which is a typical AGN SED spectral energy distribution, we can see that the emission extends from the radio up to the X-rays, hard X-rays, and even gamma rays, so even to the high energies regime. Now, what is the AGN structure? The AGN structure is a really tough topic, and there is still matter of debate about it, but for the moment we can stand with this picture, which you can see the various AGN components. You can see the jet. The jet is responsible for the radio emission in the radio loud class of objects. However, it contributes also in X-rays. You can see the narrow line region, the broad line region. You can see this donut-shaped dusty region, which is the torus, and at the center we have the accretion disk and the central black hole. Now, this picture is interesting because it is related to a certain class of models trying to explain the various subclasses of AGNs in terms of differences in the viewing angle rather than intrinsic differences. Okay? What is the origin of the optical UV emission in AGNs? The accretion disk. Indeed, if we do the simple assumption that the accretion disk is geometrically thin and optically thick, then it is possible to prove that each annular region emits as a black body at different temperature. Okay? So in this sense, we can think that the optical UV spectrum is essentially the convolution of black body spectra at different temperatures. You can also prove that the bulk of radiation is emitted at few Schwarzschild radii, so very close to the black hole, and that more massive black holes are characterized on average by cooler accretion disks. Now, the X-ray emission in AGNs is related to the optical UV emission. Indeed, optical UV photons emitted from the accretion disk, they interact with the hot electrons residing in the corona. Here we assume the corona to be spherically symmetric, but this is I would say, a zero-order approximation, but for the moment it is okay. And they are energized up to the X-rays by means of inverse compound scattering, and the result is a power law-like component, a power law-like spectrum in the X-rays. Okay. Now, the study of the X-ray to UV ratio in AGNs, it is usually done in terms of the alpha X index, which is essentially the log of the ratio between two monochromatic luminosities, 2 kb and 2500 angstroms, so X-ray and UV, and it has been found in literature an anti-correlation between the alpha X index and the UV luminosity, as you can see also from the plot on the left. However, this correlation is a byproduct of the well-established positive correlation between the X-ray and UV luminosity. Okay? Now, these two relations are of fundamental importance because they tell us about the physics underlying the accretion disk corona system. And every model which wants to explain such a system has to be consistent with these two relations. Now, of course, this relation is affected by dispersion, and the main contributions are radio-loud AGNs because of their enhanced X-ray emission associated with jets, and this fact would place them above the average relation. Broad absorption line AGNs, even though they are believed to be characterized by the same underlying continuum, absorption makes them X-ray weak, so this fact would place them below the average relation. Intrinsic X-ray weakness and variability in UV and X-ray. And considering variability, once you select only simultaneous ultraviolet and X-ray observations, you are essentially left with two contributions, an intra-source contribution and an inter-source contribution. The former due to variations in the X-ray to UV ratio within individual sources. The latter due to variations in the X-ray to UV ratio among different sources. Now, the sample we used to perform our data analysis has been the multi-epoch X-rays in individual AGN sample, and we have built it by cross-matching it with two long digital sky survey catalogs, WLEAD 7 and WLEAD 12. with the data release 6 of XMM. Moreover, we provided it with black hole mass and information, volumetric luminosity estimates coming from two catalogs of quantum properties by Shen and Kozlowski. Now, since we want to perform the X-ray to UV ratio, we need simultaneous X-ray and UV data. Since we want to avoid the spurious contributions of the non-simultaneity of data in the two bands, and for this purpose we cross-matched the MAXS2 with the XMM optical monitor, the individuals ultraviolet source sample 3, and we obtained more than 1,300 observations for more than 900 sources. Okay? With this sample, I would call it parent sample, and in that you will understand why. We studied the alpha-X and UV relation, and you can see that the two quantities are anti-correlated as predicted by the theory and as suggested by works in literature, with a dispersion of roughly 0.14. Now, in a slide I will show you that it is actually possible to decrease the dispersion of the relation by carefully selecting the sample. And in the last slide of this talk, you will understand why it is so important to decrease the dispersion of the relation. Okay? I defined by carefully selecting the sample a reference sample, which is of course a reduced one with respect to the previous one. We confirmed that the negative correlation between the two quantities and the slope and the dispersion, as you can see, has decreased with respect to the previous case. Now, the set of constraints I applied to the sample are essentially related to the first slides of this talk. Essentially, I excluded radio loud and dot absorption line AGNs because of the reasons I explained to you at the beginning, and took into account the effect of intergalactic neutral hydrogen absorption, and I set up a condition on the X-ray photon index. Essentially, I selected only non-absorbed excursions in the X-ray. Okay? Now, the goal of our work is to establish the best set of constraints in order to decrease as much as possible the dispersion of the relation. Now, in order to understand what is the contribution of intra-source dispersion, so variations in the X-ray to UV ratio within individual sources, we performed an ensemble structure function analysis. Now, the structure function is a powerful tool in order to perform variability studies. It has been extensively used in literature. Here, the structure function is defined in terms of the alpha-X index, but in principle you can define it in terms of fluxes or magnitudes or whatever you want. And as you can see from the structure function is a function of the time lag and gives you an idea of the contribution of the variability as a function of time lag. And as we can see from the red line, which is actually the structure function, the blue line is a weighted least square speed to the structure function. We can see that it increases with variations occurring preferentially at long time scales of order of 2,000 days. This means that the intra-source dispersion is due to perturbations in the outermost region of the accretion disk, propagating inwards and modulating the X-ray emission on long time scales. Now, it is reasonable to associate long time scale variations to the accretion disk. The accretion disk is much bigger than the corona. The corona would contribute on significantly smaller time scale variations. Okay, from the structure function value at long time lag, it is possible to establish the contribution of intra-source dispersion to the total variance of the relation, and we found it to be roughly 60%. But what about the residual dispersion? What is the origin of variations in the X-ray to UV ratio among different sources? In order to further investigate this issue, we correlated as a first step the alpha-X index with the black hole mass and the residual of the alpha-X and UV relation with the black hole mass. On the plot on the left, you can see that two quantities are anti-correlated, and you can essentially explain this fact remembering the geometrically thin optically thick model for the accretion disk. Indeed, more massive black holes are characterized by cooler accretion disks, and in the theory of black body effects, cooler means fainter, and so they are characterized by lower values of the alpha X index. Now, the interesting point of this slide is the correlation on the right, because this means that more massive objects are characterized by higher values of the residuals. This means that on the alpha X LUV plan I was showing you before, more massive objects tend to depart more from the average relation with respect to, the intermediate mass object. In this sense, you can add a constraint based on the black hole mass to the set of constraints I showed you before to at least try to further decrease the dispersion of the relation. Now, as a second step forward, we tried to check the contribution of the inclination. We did the width of maximum of the H beta line it has been established as inclination indicator, and as soon as the inclination increases, the width of this line increases. And there is an interesting work by you, 2012. They have built a general relativity model for the accretion disk corona system around a curved black hole. A curved black hole is a rotating black hole. And in this theory, as soon as the viewing angle increases, so the inclination increases, the X-ray to UV ratio increases as well. There is also another inclination indicator which can use the equivalent width of the oxygen tree. And to test these two possibilities, we correlated first the alpha X index with the width of maximum of the H beta, and then the residuals, again, of the relation between the alpha X and the luminosity. And we have done the same correlation for the case of the equivalent width of the oxygen tree. The rest of the correlation on the left can be easily explained remembering the work by you I was mentioning the slide before. But the interesting result is the following: is the correlation on the right. This correlation is telling us that higher inclination objects are characterized by higher values of the residuals. So again, as the case of the black hole mass, you should be in principle able to build another constraint to add to the set of constraints I was showing you before to decrease the dispersion of the relation. Okay? Now the weak point of this analysis is that we have a poor statistics. Only 50 objects out of the 600 objects in our sample are provided with these estimates of this quantity here, but this is not our fault. This is due to the fact that this line actually is available only for objects at a redshift smaller than 0.9 roughly. Now, why so much work to decrease the dispersion of the alpha X LUV relation? We said that the alpha X LUV relation is related to the X-ray to UV luminosity relation, and you want to decrease as much as possible the dispersion of this relation, because you want to use the X-ray to UV luminosity relation to build a Hubble diagram for quasars. And I'm not cheating. This has been done actually by a group in Florence. Okay, but now when you study this relation, you have to stop for a moment, because in the alpha X LUV relation, you treat the alpha X as the dependent variable and the UV luminosity as the independent one. Here, you cannot do that, because you have no physical reason to consider the X-ray luminosity, for example, the dependent variable, and the UV luminosity as the independent one. You need a regression algorithm which treats the two variables symmetrically, and once you use such a system, such a regression algorithm, actually you see that the two quantities are positively correlated. And as I was saying, a group in Florence, they have used this relation to build a Hubble diagram for quasars. The values for the cosmological parameters associated to lambda full-depth matter models they have derived are actually consistent with that of supernovas. And this method has several advantages because it can be used up to higher redshifts. It is characterized by better statistics because we have a bunch of AGNs, but there are shortcomings due to the fact that we have to stand with the dispersion of this relation. Okay? So actually, it is possible to use this relation to build a Hubble diagram for quasars, but previously you have to work to build a sample which minimize the dispersion of your relation. Okay? So essentially, the anti-correlation between the X-ray to UV ratio and the optical UV luminosity has been confirmed. Roughly the 60% of the dispersion, we can explain it as intra-source dispersion, so variations in the X-ray to UV ratio within individual sources. The remaining dispersion, you can essentially think about the black hole mass or the viewing angle, but further analysis is for sure needed. And as a last point, the X-ray luminosity, the X-ray UV luminosity relation can actually be used to build a Hubble diagram for quasars. It is not as easy as for supernova, I would say, but you can actually do it. Thank you.
Questions? Okay, just curiosity. In the plot at the beginning of the talk, it was. At the beginning of the plot, there is the spectra within the lines. Yes, maybe. Why is absent the ion line?
What kind of line?
Ion line is
No, which one?
K alpha, K beta.
Well, the K alpha is, you can actually see the K alpha. Well, you can actually see the iron K alpha line, but in the X-rays. So at 6.4 kV typically. This is in the optical. It is optical UV spectrum.
Thank you.
Well, I should
No, it's my.
because it is in the 1,000, roughly 5,000 angstroms.
Yes,
so
I have a problem with my.
no, but actually you see it. You see the iron flash line. So it's extremely important, I would say, in this case.
Thank you. There is a question.
Okay, so you said that you can use the X-ray UV luminosity relation to build an Hubble diagram for AGN, but can you give some more detail on how can you measure the redshift and the distance independently?
Yeah. Actually, I was expecting this question. Actually, you can use this relation, as you can see, but the key assumption is that there is no redshift dependence of the relation. Otherwise, you would add the spurious contribution per redshift. So you have to first assume that there is no redshift dependence of the X-ray to UV luminosity relation, and it is a good approximation. It has been verified that there is essentially no redshift dependence of this relation. And then at this point, if there is no redshift dependence, then you can, as you can see, you can simply relate the fluxes, the X-ray flux, the UV flux with the luminosity distance. This gamma actually here in this set of equations, the gamma is obtained by minimizing this likelihood function, which is a sort of chi-square function. It is modified. There is in the brackets there is a contribution in order to take into account the dispersion, but it is essentially a function minimized, and you obtain gamma, or you can also determine gamma as an average value, okay? And both methods seems to work, okay? And once you have done this calculation, then it is straightforward because you have a simple relation distance modulus, all the quantities. You have the X-ray flux, you have the UV flux. Beta first is a constant depending on gamma, and then you can fit.
Thanks to the speaker again. Okay, now it is a pleasure for me to introduce Dr. Caroline Chaplet from GSSI and INFN, the National Laboratories of Buganzasso. She is working and she is really responsible of the cosinus experiment, national and local responsible. And she graduated at the University of Applied Science of Munich and got her PhD at the Technical University of Munich. So it's a very pleasure that you are here for us. Thank you.
So thanks again for the invitation. It's really a pleasure for me to be here. As you said, hello, you hear me? Okay, now. So, okay, thanks again. And yeah, for me it's a pleasure to be here. So my name is Caroline. I come from Buganzasso. I guess we had even a meeting there some couple of years ago at L'Aquila University. Okay, so I will talk about direct dark matter searches, especially like nice dark matter searches. I will explain this later what this actually means. I'm also the last speaker, I guess, before the coffee break, so stay awake. Yeah, so let's start. So probably you all know that dark matter, like that we have it in our universe. There's evidence on all the different cosmological length scales. So going from like cosmic microwave background to large scale structures, galaxy clusters, as we have heard before. So there is very convincing evidence that we have dark matter around us. And from precision cosmology today, we actually also know quite well how much of dark matter we have. So there's about 27% of dark matter in our universe. 5% is only the matter that we know. So it's 5 times more actually that matter that we really know. And then there's this big part of dark energy where so far we have not so much an idea of. So in the end, you see we know actually quite little. And this goes even on because like how this dark matter is made of, we have also really only a little clue. So what we know that it should be non-baryonic. We know that it should be cold. It should be stable, at least at the age of the universe, because we can still observe it today. And interaction, so far, like all evidences, they are based on gravity. So this is the only, for sure, interaction that we know. And then there's possibly also one on the Wick scale or beyond. So this is actually also what we hope for, because being an experimentalist, this is the only way how you could detect it. So maybe like Newton once said that, okay, what we know is only a drop in a big ocean. Okay, so this should not prevent us from trying to find out what this particle is. So as you can see, there's a lot of theories which theoreticians put on the table. They range from some small extensions to the standard model of particles, like Suzuki, for example. But then there's also PCB axions, little Higgs. I mean, there's extra dimensions. There's a lot of things that people think about which could offer such a dark matter candidate. Then you can say, okay, I should detect it, so I should build an experiment. How I can do that? So one class of experiments is the so-called indirect searches. where you look for an annihilation product. So the dark matter particles transform to ordinary particles, and this is then the ones you detect in the detector. So this is typically done with telescopes on Earth or also satellites on the universe. This is so this indirect searches. Then there is another big class, which is the experiments at colliders, which we call the production experiments. And there you look for like photons or electrons and positrons, like a bell, for example, converting to dark matter. And there you actually look for a missing energy. And this is, okay, the collider searches. Then the biggest maybe group of dark matter searches is the so-called direct dark matter searches. This is also the ones that we concentrate on then for the rest of the talk. And there you actually look for a scattering. So you have the dark matter particle scattering off your standard model particle, and then you get a nuclear recoil, and this is actually the signal you then detect. And there's a really big group of experiments which built up in the last 15 years, and I will come to this later. Okay, so in such a direct dark matter search, what is the most basic assumption is that you have particle-like dark matter scattering of standard model particles, and this is also the most common case. I mean, you have it scattering off, and then you have this nuclear recoil, which you measure as I said before. Okay, so then if you have such a process, what is the rate? So what do you expect from such a dark matter particle scattering? So the rate is given that you have here the number of target nuclei, then you put in the dark matter flux, and also they will also do this distribution, as well as also some cross-section for this dark matter part. Okay, you can do then the differential rate, where you then have the integral over this velocity distribution, and there's the cross-section term where you get an A squared proportionality, so heavy targets is preferred. And there's also the torque factor going in. And of course, here again, we have this velocity distribution of this dark matter particles which interact in your detector. Okay, so you plug in numbers, for example, for a light dark matter particle of 10 GeV, a more heavy one until 1000. So this is what I show here in this plot. So this is the differential rate versus the recoil energy. And you can see, I mean, this is really rare interaction rate here. I mean, the best like current limit coming from the xenon 1 ton experiment, where they have a 1 ton and a year detector, only 0.01 counts per kV. So this is really rare. This is a couple of events in a year in a ton detector. So this is really little. If you go on, I mean, and you see also here on the x-axis, there's this recoil energy. This is in the range from a couple of kV to a couple of 10 kV. So this is also very low energy. So you need very good detectors with a low energy threshold. And also, as you can see, I mean, the spectrum that you expect from a dark matter particle is flat and featureless. I mean, it's quite difficult also to search for it because it's very close to the threshold. I mean, you don't have a peak or nothing, you have just a spectrum. Okay, but this is not the only signature you expect from such a dark matter particle, but there's also what we say is the modulation expected, because like beams sit on the Earth, move around the Sun, and move through this dark matter halo. And what you experience is then with 1 year of period, that you go half a year with this dark matter halo and then against. So you have actually a variation in this velocity, which leads then to a variation in also the rate that you expect of your dark matter particles scattering in the detector. And this actually variation in the rate, so this so-called modulation signature, is really a signature. So this could be something which is a smoking gun in direct dark matter searches. Okay, so the signatures, as I said, so we have modulation, so the rate versus time varies. This is one signature. The other one is, like doing a counting experiment, you can also say, I have a certain background in the region where I look for dark matter particles, and on top of that I could have the signal, which if I have a big enough detector also is sensitive to this modulation. Then in reality, it's not one or the other, but you can have also somehow exploiting both of the signatures, the modulation and the counting. So we don't have a real separation about experiments doing only modulation or doing only counting. So there's some synergy. Okay, and just to show you that direct dark matter searches is really a worldwide effort, and this is like just all experiments in this different underground labs. So there's Snow Lab in Canada, for example, and in Europe we have in France, Spain, and Italy, big underground labs where there's a bunch of experiments. And then there's also in Korea, there's Yangyang, and then Jinping is a new underground lab in China, and also a Amioka mine in Japan. So there's really a big group of experiments now existing, and one is even at South Pole, which is called Diamite. And yeah, so all these experiments, they use different techniques and different targets, and I would like to give you some overview on the different channels you can actually detect when you try to plan an experiment for direct detection of dark matter. So first of all, you know, I mean, the signals you can measure is ionization in case you have a semiconductor, scintillation in case you have a scintillator, and then there's the phonons, so the heat signal that you can measure if you have an experiment which is at millikelvin temperature. So you can actually measure the heating up of your target when there's the interaction taking place. Okay, so typically, like the only one which is 100, like not quench channel measurement of the deposited energy of the particle in the detector is when you measure the phonon signal. For scintillation, typically we have efficiency of 1 to 10%, depending on how good is your scintillator. And for semiconductors, if you measure the ionization, it's about the 10%. So the ionization and scintillation is quench channels on the phonon. It's not quench channels. Then let's have a look what the experiments do what. So we have semiconductor experiments with Fusion, CDEX, and DAMIC. They use germanium and silicon. Then there's superheated liquids, which is this bubble chamber experiments, which is like storage experiments with PICO. This is in Canada. And then there's also now novel gas detectors doing that. Then we have the big group of experiments doing scintillation detection only. So there's most famous, we'll talk about later, Dama Libra with sodium iodide and cosine, and things with cesium iodide. And then there's also single-phase noble liquid gases, which is deep and X mass. They use argon. Okay, then you can say, well, they detect only one channel, so only light or only ionization, so they have then a one-dimensional energy spectrum, and this is where they extract the information of. But you can also say, why not measuring two channels? Because this might also have an advantage, and okay, echo, this is what experiments do. So there's this very popular liquid noble gas detectors with xenon, lux, Canix, and backside. They use xenon or argon. So this is these TPC detectors, like there's the liquid or liquid gas inside, and you measure the ionization and the scintillation light, and this allows you actually to do particle discrimination. So you can then understand, is this a nuclear recoil, a possibly dark matter, or is this only electron scattering and the background? So with this two-channel technique, you can understand what is actually your type of interaction. Same is true for the semiconductor calorimeters, which is also measuring two channels, so ionization and phonons. They are super CDMS, which is American, and Edelweiss, which is in France, both with germanium. And yeah, they also have the same possibilities as this liquid noble gas detectors. They can do particle discrimination. The third one here is then scintillating calorimeters, which is measuring scintillation and the heat signal. And there's like Crest, a very good experiment for low mass dark matter at the moment, and also proving later. So, and yeah, as I said, I mean, the advantage of doing a two-channel detection is that you can separate your dark matter signal from the background. The single-channel detectors cannot, so they measure both. And somehow it's like that single-channel detectors, they do modulation searches, they do big target masses, and they search for the modulation signal, whereas if you do the dual-channel approach, you can do easily both. I mean, somehow the constraint for doing a modulation search is, of course, that you have a big detector, because otherwise you are not sensitive to this low variation. Right. Okay, so now we've heard about all these experiments, different techniques, different targets. In the end, I mean, everybody, the producers are excited and how this results is actually compared. And this, in the dark matter community, we do in the so-called dark matter landscape plot, where you have here the dark matter particle nucleon cross-section versus the dark matter particle mass. And in such a plot, if you draw a line, which we call a limit, you exclude the parameter space above, and you say, yeah, I exclude that there's a dark matter particle with 30 GeV and 10 to the minus 2 cross-section. Okay, in case you have a positive signal, because you see something in your detector, you will draw an island, and then, okay, this is with a 1 or 2 sigma uncertainty, and then you say, yes, my dark matter particle has 10 GeV and a cross-section of 10 to the minus 6, for example. So this is in case of positive anything. Now, I mean, if you want to say, I want to improve my experiment, how can I do better? So if I want to improve going to low mass dark matter, I should go in that direction, and this I can only do if I do an experiment which has a very good energy threshold, like talking about 1 keV and lower. And this, then you can push your limit or sensitivity in that direction. In case you want to gain in cross-section, what you have to mainly do is do your detector bigger. So this is, for example, what all these liquid noble gas detectors do. They started off with 10 kilograms and 100, and now xenon is doing 1 ton and already preparing now for the n-ton case. So if you want to go down here, this you can do only by increasing your mass. Okay, so let's have a look what is present status. So now you see it has many lines because there's many limits, no observational discovery yet. And all these blue lines here down, this is the liquid noble gas detectors, as I said, so they are very good with increasing in exposure and big targets, so they are very sensitive. And then you have this experiments here, which is CREST and also NUSG and Edelweiss, which is experiments which have a lower energy threshold, so they can do good for low mass dark matter. And yeah, and then here you see an island, which however is yet already excluded by the experiment itself, and this was just a wrong interpretation of a background. Okay, but then now I want to focus on one experiment which I so far didn't mention, which is Dama Libra. So Dama Libra uses sodium iodide detectors, and they actually measure modulation, and they have a signal. They have this modulation signal, and they can draw the two islands here. And this is the two islands for the dark matter interpretation of their site. And you see they are very much in conflict with all these other limits. I mean, they are far off. I mean, he has many orders of magnitude there, which is here in between the xenon experiments and them. So actually they are by far excluded. But still they go on seeing this modulation. And yeah, so the situation in the dark matter community today is somehow like that. I mean, we have no signal for most of the experiments with even very high sensitivity today. And yeah, they exclude everything above, and yeah, this is the status of them. Then there is now experiments like CREST and NUSG, Super CDMS, they push to lower dark matter masses, and they are starting to be also quite successful in that, so this is also very interesting. But then there is this Dama signal, which I've shown you before. I mean, there's two islands here, which are excluded by everybody else, but they are there. And they produce a very contradicting situation in the field because, I mean, nobody says this is wrong what they see, and it's in contradiction, so it needs explanation. Okay, then you can ask, is this really valid to put all experiments in one plot and then compare one by each other? And actually the answer is no, because in order to put your limits or your discovery in such a plot, you have to put in model assumptions. And mainly they come from the dark matter halo and the velocity distributions, or this term here, as I've shown you before. And you have also some assumptions on the particle physics, because of course you have to say what kind of interaction I want to look for. In this plot, which is assuming the standard scenario is spin-independent interaction. And yeah, so you see, you have to put in quite some assumptions in this plot, and so the end is not so valid very much to compare one experiment to the other. And a good thing maybe to finally also put a statement to Dama is then to make an experiment with at least the same target material, so you exclude some of these assumptions that you put on. And this is also done in order to resolve this contradicting situation that we have at the moment. Okay, so the target Dama is using is called sodium iodide. So this is a two-component material, sodium and iodine. So there comes also the slides from, which I was saying before. And yeah, so sodium iodide is a very good scintillator. You maybe all heard about it. Doped with thallium at room temperature. The scintillation spectrum also fits very well to that what photomultipliers like. So this is very nice. And then there's also the crystal, which is, if you talk to people producing crystals, this is very easy to grow. It's commercially available. So this is quite straightforward. You can buy big blocks of 10 kilogram of such crystals, like shown here. And okay. Then how the detector looks like is also quite simple, because you have your crystal here. Once you have a particle interaction, you get light. The light is detected with the photomultiplier, and it's done. Okay, there's also some drawbacks of this sodium iodide. One is that it's hygroscopic. So if you expose it to normal air, like here, the humidity will destroy completely the surface, and this will also harm the scintillation. So you have to always be very careful to handle it in controlled atmosphere, for example in nitrogen. And another bad thing, especially if you want to do dark matter, so as I told you, we search for very rare events. If you want to do dark matter, you should have a low background, so you should try to eliminate as much as possible natural radioactivity. For example, this potassium-40, which is a very bad background also in sodium iodide, because it's chemically very similar to sodium. So this potassium-40 makes electron capture, and what you get together with this 1.4 MeV gamma is a 3 keV Auger electrons, and this is actually a background right there where you look for your dark matter signal. So when you want to do a sodium iodide experiment for dark matter, you have to be very careful with your material selection during the crystal growth process. Okay, as this situation with the DAMA results is up for about 20 years now. I mean, now people started to be worried about it and started to do sodium iodide experiments all over the world. So you can the map. So we have a sodium iodide experiment in Spain, in Canfranc with Anais, and in Gran Sasso in Italy there's DAMA, the experiment which has this modulation result, and Salerno and Putin Institute set up experiments. Then there's in Korea, Kinston Fossil, in Japan there's Picolon, and then there's a second site for the sub experiment, which is also in Gran Sasso here in Australia on the southern hemisphere, and there's also one in South Pole in this ice cube. Okay, so now let's tell you what is actually the DAMA experiment and what is their signature. So in the end, DAMA Libra has 250 kilogram of sodium iodide crystals of the thallium. They measure the light signal. This is a signature detection. There is no discrimination with the gamma against nuclear recoils as expected for dark matter. The energy threshold, just recently the published data, is now at 1 keV electron equivalent. So this is the threshold for electron interactions. Then they are data taking since 1996. Maybe most of you went still to school or kindergarten, so this is really a historic experiment. And yes, they have this evidence I was mentioning before. Here's a sketch of their setup, so it's quite easy or primitive in comparison to a lot of other experiments existing today. So they have a lot of shielding around, polyethylene, lead and copper, and then inside here you see these blocks of crystals. Each crystal is 9 kilogram, and then they pair it with these 2 phototubes from 2 sides, and they are all sealed in this copper container for keeping them not in contact with normal air. This is their result. So here you see now this residual rate versus time, and here's the DAMA phase 1. It's 2003 to 2010, and here you see this modulation, annual modulation, up and down, up and down, up and down. Then there was an interruption because they upgraded to new phototubes, and then there's DAMA phase 2, which is 2011 to 2017, and you see again, you observe nicely this modulating rate, and this also after the interruption just perfectly started again, so it's not even, we cannot say, both maybe something in the setup or whatever. No, it's just perfect. So there's now a total exposure of 2 ton in years for phase 1 and 2, and the significance for their signal is more than 11 sigma, so this is really very convincing, so you cannot discuss it away. Yeah, and they claim that this is dark matter. Here's the energy spectrum from this phase 1, so you have here the rate versus the energy, and yeah, the threshold is around 2 keV here, and you see then here it's very flat. There's a small bump which comes from the potassium, and then they have around 1 count per keV kilogram a day of events in their detector. This is very low background because they managed to have very clean crystals with little of potassium, less than 20 ppb, and also uranium and thorium contaminations is at a very low level. So they did a very good job in doing a clean crystal. Okay, the modulation actually they observe only in this energy window from 2 to 6 kV electron equivalent. So this is actually where they have this modulating rate. And yeah, so here I show you now this modulation amplitude again versus energy, and you see in this window here they observe it, and in gamma phase 1 the threshold was at 2 kV. Now in April they published new results from 6 years of running with a lower threshold. Like you can see here, this is now the new data, so to say. They added with a 1 kV energy threshold, and the modulation is still there, and you can see also now the shape how this goes on, which is quite interesting, because it excludes actually that it can be the standard spin-independent dark matter interaction. So this is actually quite a nice information. Okay, you can then say, well, maybe it's not right, maybe it's something going on, whatever, you don't understand your background. But AMA did a lot of work in the last 20 years to somehow answer to every question which was raised by theoreticians, by experimentalists, because nobody believes it, because that's why all others excluded. So one check you could do, for example, then is checking single versus multiple hits, because dark matter, as it interacts rare, you don't expect to scatter more than once in your detector. So then you see here, like with single hits, you have your modulation, but multiple you don't have. And yeah, there's plenty of such tests they show and did in hundreds of papers within the last years in order to justify what we see. So in the end, maybe it's a smoking gun evidence, who knows, statistics is right, the period fits perfectly to that what we expect for dark matter, same as for the phase. And as I said, I mean, since many, many years, there's no non-dark matter explanation which is convincing, which is today. Okay, so then you can say, well, let's do such an experiment and see if we can reproduce what gamma does. To do that, you should have at least 2 kV energy threshold, this low background of 1 count per kV kilogram a day, and a large detector mass, at least a couple of 10, if not 100 or 200 kilograms. Then you can say, I do a bit better than gamma does. I mean, I, for example, can add active veto to reject further this potassium background. I can put a muon veto to exclude muon-induced background, which is always a criticism to gamma. And you can also say, well, why not doing also particle discrimination, right? Because there's like plenty of other experiments in the field which do that. Maybe we could also implement this for sodium iodide. Okay, so let's go through some of these experiments which exist today. So there's ANAIS, has 112 kilograms of sodium iodide, measures also only light, like gamma, is in Canfranc lab in Spain. They also don't have discrimination. They have a threshold which is lower than that of gamma of 0.1 kV electron equivalent, and they are taking data since last year. They have something in addition, so they have a muon veto, which is nice. And yeah, here you can see their setup. So inside there's the crystals, and then there's shielding, and then there's here this muon shielding, and then additional neutron shield outside. Here you see a person mounting such a detector, like in a copper container with a tube on the tube. Okay, so some of their results. So here there's the energy spectrum for different crystals, and you see, I mean, this is actually energy, yes, the resolution, and you see they have a very high light collection in all the modules, like this one, they show about 15 photoelectrons per kV, so this is a factor of 2 better than gamma does, so this also results in this better threshold they have. Yeah, they also have a quite good understanding of their background. Like here you see this energy spectrum, but I mean gamma is at this 1 kV kilogram a day here, and they have more 2, 3, 4, so they are like a factor 2 to 4 off with their crystals from what gamma has, so their crystals is not as clean as the ones of gamma. And yeah, so this is a projection of them for the next 5 years of data taking. So now they have completed 1 year, so they will go for another 4. And then you can see, I mean, this is the islands of gamma which they just arrived to exclude. Okay, then there's another approach which is called DMIs. This is a 17 kilogram sodium iodide detector, actually it's 2 modules. Again, only light located at the south pole, and the threshold is 4 kV, so this is now 4 times more than gamma has. And they are running since 2011, and they publish data, and they have no no evidence in their data. But what is peculiar about DMIs is that it's employed in the ice cube zone where they have like strings running down about 2.5 kilometer in the ice, and down there then they have the sodium iodide detector. And yeah, so this is the only up to now existing sodium iodide experiment on the other hemisphere. And this is interesting because you might imagine that there's some other muon-induced background or coming from the sun, whatever background, which somehow also does some modulation because you move around the sun and could maybe mimic this what Dama sees. So if you then go to the other hemisphere, this background should like just change in phase as expected, but dark matter should not. So this is a nice add-on to what Dama does. Okay, this is the background spectrum of DMIs. So you see, they have a good understanding of the background, but their background is pretty high. And yeah, this is an exposure of about 60 kilogram years. So before we heard Dama has 2 ton years. And yeah, the energy range is from 4 to 20 kV, so this is also a bit higher than Dama does. If you now calculate, or if you have a look at this residual rates or the modulation amplitude versus the energy, you see blue, this is again what Dama has here from phase 1. And yeah, the DMIs, the 2 detectors, 1 and 2, in red and green, you see with large error bars at their results. So this is not at the sensitivity level now to give an answer on if Dama is right or not. And here you see also the limit. I mean, this is again the Dama islands, and you see they are right here. Now they plan an upgrade to go to 500 kilograms, and with such a detector running in 2 years, they might be able to give an answer on Dama or in the near future. Okay, then third experiment I would like to talk to you about is cosine 100. So this is maybe the most exciting one at the moment. They have 100 kilograms of sodium iodide. They, again, light only. They're in Korea. They have a 2 kV energy threshold, and they run since 2016. They have also liquid scintillator vetor and a muon veto, so this is 2 things more than in Dama, and there's a sketch of the setup. So again, here inside, they're always a bit the same, like arranged like an onion. In the middle, there's the detector, then there's the shielding outside. Here they have this liquid scintillator around the crystals, and this allows you, when you have this potassium decay, like you have this gamma of 1.4 MeV going to the scintillator, producing their light, and then you can reject any other event you would follow, like this 3 kV or shear electrons, for example. And this is a way of reducing the background further. Here you see their background spectra from about 1 year of data taking. So for 4 different crystals. Here again I draw the Dama line for comparison. And you see they are also a bit off from that what Dama achieved. And yeah, especially they have this left to 10 contamination. And yeah, they're presently working on getting also cleaner crystals. But okay, this is the crystals which are running at the moment and which they also would like to use for physics results. And this is the result they hope for. So running these detectors for 5 years. So now we have completed almost 2. For 5 years should, following their projection, allow them to arrive at the sensitivity level of Dama. Okay, then last one I would like to talk about is Sabre. Sabre is another experiment, Dama-like, all the same, 50 kilogram, has 2 sites, one in Transasso and one in Australia, which would be then also southern and northern hemisphere, which, as I said before, might be interesting for modulating backgrounds. And yeah, they are presently not yet running, so they are doing the instrumental setup and trying to put up a proof of principle detector. Yeah, they aim for a 2 kV also energy threshold, and they have their own crystal production program because they aim for very clean crystals. Here's just a sketch of their proof of principle that they hopefully will manage to do within 2018. So here they have 1 crystal in a tank again with liquid scintillator, and using this liquid scintillator veto as shown here, I mean, we have this peak from the potassium at 3 kV. if you then put the video on, you can reduce by a factor of 10 the background you expect to have in such a setup. This is once they manage to set up this 50 kilograms and then run for 3 years, this is the expected sensitivity, which would then be at the level of sound. And assuming a background which is 0.2, so this is a factor almost of 5 better than what DAMA has at the moment, and this has to be also fully demonstrated. Okay, last thing, I promise. Cosinus is the project I'm working on. We also use sodium iodide. We don't only collect the light signal, but we do two-channel approach. As I said to you before, this is very interesting because we can do particle discrimination. So we measure the light and the heat signal, so doing a cryogenic detector at about 5 millikelvin. We are located at San Saxo, and yes, we can do particle discrimination. The threshold goal is 1 kV. And this doesn't mean 1 kV electron equivalent, because as we run a bolometer and measure the phonon signal, this is actually the real energy, so not the quenched one, because, for example, for sodium and iodide recoils in such a sodium iodide detector, you expect the quenching factor, which of course then you have to account for, and this is around 3, a factor of 3 for sodium and 10 for iodine. So if you want to translate this for the threshold for sodium, this would be around 6 kV. And 10 for iodine. Okay, here you can see such a cryogenic sodium iodide detector. So this is the crystal here, which is attached to a thermometer, which is able to read this very low energy depositions by the dark matter or other particles. And here you can see it again, and the sketch. So this is the crystal, and around the crystal we have another detector, which is a silicon beaker, which works as a cryogenic light absorber. So we detect with the silicon beaker, which is shown here, we detect the light. And then we have here the two channels. We did our first proof of principle detector already in 2016, where we arrived at around a threshold of 8 kV. And the light yield is very good, so it's around 13%, so this is more than what we ever expected. At the moment we are working on reducing this energy threshold further, so now we arrived at the last prototype at around 5 kV, and we are just in the transition now to really become also an experiment. Here you can see just a sketch of a plot of what does it mean having two channels. So you have the two-dimensional plot. Here's the light yield parameter versus the energy, so the heat channel, let's say. So this event distribution up here, this is the electron gamma events. You have here from calibration source of americium, the 60 kV line, 20 kV line of iodine escapes, and there would be the 3 kV Auger electron from this potassium decay. And now if you ask for, where I expect now sodium and iodine recoils as dark matter should do, so you have the quenching factor to take into account, and then you have these bands down here, the blue one and the green one, where you would expect now the dark matter interaction. And this is very nice because it allows you really to disentangle the background from the signal, and also to give actually an information on the interaction channel, because this, like in DAMA, you cannot do, because you don't know is the interaction with the electrons or the nucleus. You have no information, and with a two-channel detector you can add this information on the interaction. Okay, just a projection also for cosinus, where we can go with 100 kilograms of exposure. So this, as cryogenic detectors have this lower threshold, especially for nuclear recoils, and what you then need in this, assuming of course also a standard interaction, you need a lot less exposure. So we can go with 10 detectors of 100 grams, and running 1 year we can already set this limit here, and by 2 orders of magnitude check actually the gamma signal. But of course this also puts always into the assumption that you do the spin-independent interaction. If you want to exclude, for example, with a cosinus detector, model-independent DAMA, you would have to go to 1,000 kilogram gas, which would mean like running 3 years with 20 detectors. Okay, this brings me to my summary. So DAMA presents since 1997 this observation on the evidence for dark matter by this modulation signature. We are now in 2018, and the situation is still the same, so they lowered the threshold, they still see the modulation, but other experiments, they exclude their results, so we have this contradicting situation which asks for clarification. And yeah, as I've shown you, I guess there's numerous of experiments now up which are using sodium iodide detectors, but they all so far do not have the same background level in their crystals as DAMA has, so this makes actually it very difficult to verify, cross-check, or whatever you want to call it, the DAMA experiment. And yeah, so in the end we have to be patient and wait another bit, because I guess experiments will need another 2 to 3 years until they really maybe arrive at the level that they can give an answer on if DAMA is right or not. And yeah, stay tuned how the story goes on. Thank you.
Questions?
I have a general question on the background of dark matter. This experiment was so hard because dark matter is very fully present with like neutrinos, or also because it's rare. I mean, I know it's most of the universe, but there is even space also here, or we find it in clusters.
Yes, I mean, it should be like, as it is doing gravitational interaction, I mean, it's assumed to be like as a halo around us, and then, I mean, the interaction is very rare. I mean, there's not little particles. I mean, the flux is very high. I guess if I remember correctly, if you put in 100 GeV like matter particle, there's 3,000 passing your thumb in a second, so that's quite a lot. It's not, I mean, as neutrinos from the sun, but there's a lot of dark matter around us. It's more that we don't know, I mean, what is the interaction, and as it looks like it's not on the big scale. I mean, this is what we always hope for, that I mean, on the normal big scale we know now. I mean, this is a bit the problem, we don't know it yet. And as I've shown you, I mean, this xenon experiment, this is cross sections 10 to minus 46. So this is really, I mean, maybe I'll show you again the plot, then you see also where you would arrive. I mean, here, for example, what we always show here, this is this neutrino floor. This is where you expect scattering of neutrinos on the nucleus, coherent neutrino nucleus scattering in your detector. And the xenon experiment, for example, arrives there. And this is pretty astonishing, I would say. I mean, for the low mass region, we are not yet there. You can see this experiment, there are quite some orders of magnitude off. So this is minus 46 to 41. Yeah. And the problem, I mean, or let's say, I don't know, it's not a problem, but it looks like somehow that this WIMPs is also always called this kind of dark matter particles, so weakly interacting massive particles. Seems out that the parameter space is more or less starting to be ruled out. So maybe one would have to think about some other possible candidates, which, I mean, is not the standard WIMP dark matter, I guess. I mean, I've got this feeling that dark matter might not be the WIMP-like.
Other questions?
Can you hear me?
Yeah.
Okay. Just a curiosity, what about the calibration of very low energy for these crystals?
Okay, I mean, for this sodium iodide searches, I guess it's not so difficult because you have this 3 kV bump from the potassium you could calibrate, and also for in ANA, you see this 900 eV line. I mean, they can somehow do it, but of course, I mean, they are also, how to say, I mean, this is for electron gamma events. Then you look for dark matter which should do nuclear scattering, because you don't expect to do electron scattering for the dark matter. Then for nuclear scattering, the story is already different, because in the sodium iodide experiments, you have to assume these quenching factors. And these quenching factors you would have to measure at neutron scattering facilities, where you then really go down to these energies, and this is also done. I mean, this is done. But then also on the other hand, it's maybe not so important, because if you see a modulation, you see the modulation. If this then is 1 or 2 or 3 factors off in energy, you can say, okay, but I see the variation in the rate, maybe I'm not so much, it's not so dangerous if you're wrong with your energy scale. However, for all these other searches, I have not too much in detail explained to you, like the xenon experiment, or also the solid state detectors like CREST and CDMS. For them, it's very crucial, the energy scale, because, of course, you define the window where you look for your recoil signals, like you define it and then you look at it. So there you have to be very careful, and like for CREST and CDMS, this starts to be very difficult, because if you have an energy threshold, like CREST has now about 25 electron volts, so this is very low, and energy calibration becomes a challenge.
Okay, if there are no questions, let's do speaker again. So now there is the coffee break. We will recombine at 11:45.